Have you ever driven past a massive oil refinery or a chemical plant and just wondered, what is keeping that whole incredibly complex thing from going terribly wrong? Well, I can tell you, it's not luck. It's a very specific language, a whole way of thinking that's designed to stop disasters before they can even get started. And to understand that language, we've got to start with one big question.
Right. How do you actually do it? How do you manage something so huge where just one little mistake could be, well, catastrophic? The answer is all about learning to speak the language of safety. And the first, and probably the most important word you need to know in that language, is risk.
So, before you can even think about managing risk, you have to know what it is. And in the world of industrial safety, risk is not just some vague feeling you get. Nope, it's a precise, calculated concept.
And here it is. This is basically the fundamental equation of safety. See, risk isn't just one thing. It's always a combination of two different factors. First, the probability of failure, or POF, which is just how likely it is that something will break. And second, the consequence of failure, or COF, which is how bad things will get if it breaks. You just can't understand risk without looking at both sides of that coin.
Let me break it down with an example we can all get. Think about a car tire. The probability of failure, that's the chance your old, worn-out tire might get a puncture. Okay, seems pretty low. But the consequence of failure, that's not just getting a flat tire by the side of the road. It's that tire blowing out when you're doing 70 on a packed highway. Suddenly, the whole picture changes, right? Even something that's not very likely to happen can be an unacceptable risk if the consequence is a total disaster. You have to think about both.
So we just defined risk using the word failure. But what does that word failure actually mean when the stakes are this high? Let's drill down on that.
Okay, so technically, failure is just when a piece of gear stops doing the job it was built to do. A pump doesn't pump anymore, a valve doesn't seal shut. That's failure. But in the kind of places we're talking about, it often means something much more specific and, frankly, much more scary.
This quote really gets to the absolute heart of it. For these big industrial sites, the number one thing they worry about is loss of containment. And that's just the professional way of saying a leak. Whether it's oil or natural gas or some nasty chemical, the second it gets outside of the pipe or the tank it's supposed to be in, you've got a major failure with potentially devastating consequences.
So how does that loss of containment even happen? Well, it's almost never some big sudden event out of the blue. It's more like the slow creeping process. We're talking about stuff like the metal walls of a pipe getting thinner and thinner over years of corrosion. Or tiny little holes, what they call pitting, that slowly drill their way through the metal. And those small points of damage can grow into cracks. And a crack can eventually lead to a catastrophic rupture. These are the real-world boogeymen that engineers are constantly on the hunt for.
All right, so we've identified the threats. How in the world do experts decide which ones need the most attention? Well, they don't just guess. They have a whole structured toolkit they use to analyze the risk.
Now, the really important thing to get here is that this whole process is built on systematic, evidence-based methods. It's all about stripping emotion and gut feelings out of the equation and replacing them with cold, hard analysis. The goal is to figure out exactly what's most likely to fail and what's going to cause the biggest mess if it does.
And they basically have two main ways of doing this. On one hand, you have qualitative analysis. You can think of this as relying on the deep wisdom of a seasoned expert, someone using their years of experience to just categorize risks into buckets like high, medium, or low. Then, on the other hand, you've got quantitative analysis. This is all about the data, using really complex computer models to calculate an exact numerical value for risk. Both are absolutely essential tools in the safety toolbox.
Okay, understanding the risk is one thing, but that knowledge is pretty useless if you don't do anything with it. And this is where all that thinking and analysis gets turned into a real, concrete plan of action.
This right here is the process that makes it all happen. Risk-based inspection, or RBI. And notice how that definition brings everything we've talked about together. It uses both the probability and the consequence of failure to build a smart plan. So it's not about just inspecting everything all the time. It's about inspecting the right things at the right time.
And the process itself just makes so much sense when you look at it. Step 1, you figure out the credible threats, those damage mechanisms we saw earlier. Step 2, you actually assess the risk for each of those threats. Then, the really crucial third step, you create an inspection plan that focuses your time and money on the highest risk stuff. And finally, for anything that's still too risky, you take action to mitigate it.
And that word, mitigation,
That's the whole point. That's the end game. Mitigation just means you're actively taking steps to make things safer. So that could be something like replacing a piece of pipe that reduces the probability of it failing, or it could mean building a bigger, stronger containment wall that limits the consequences if it fails. See? You're attacking both sides of that risk equation.
So after all of this analysis and all the planning and mitigation, what's the goal? Are we trying to build a plant that has absolutely zero risk? Well, the answer might not be what you think it is.
Here's one of the fundamental truths of engineering and really of life. You can't eliminate all risk. It is impossible. A car will never have zero risk of an accident, and a chemical plant will never have zero risk of a leak. So the real goal of all this work is to get that risk down to a level that we as a society decide is acceptable. But that, of course, raises a pretty big question. Who gets to decide what acceptable is?
The industry has a specific term for this idea, ALRP. It stands for as low as reasonably practicable. And it's basically the principle that you should keep working to reduce risk until the cost, whether that's in money, time, or just sheer difficulty, of making things even a tiny bit safer, becomes totally out of whack with the tiny benefit you get. It's a pragmatic, real-world balance.
And that, right there, leaves us with a really fascinating and difficult question. This whole incredible system of safety is built on this shared idea of what's reasonable. But when we are talking about our own safety, about the potential for a real disaster, what exactly is reasonably practicable? That's a question that engineers and regulators and really all of us have to wrestle with every single day.